I'm Chris. It's a great pleasure to be here. What I want to do over the next about 20 minutes or 15 minutes is share with you some of my excitement about this new generation of data processing systems we've been building in my group that we call trained systems. And I hope to tell you why we're excited about what they can do, that is, if they can accelerate science, which I'm going to talk about during my talk, and also try and give you a sense of why they're so challenging to build and they keep us up at night and the weekends slaving away on these systems. But before getting to the challenges, I want to talk a little bit about how science is done. So to do that, I brought one of my buddies here, Isaac Newton, one of the great scientists of our time. Someone who invented, calculus in order to solve physics. I mean, it's really just a spectacular person. So Isaac, after he, did all of his great discoveries, he wanted to disseminate them to the world. And like most scientists, he wrote a book. Okay? So he wrote this very famous book, Principia Mathematica. He set out his ideas, and then he distributed it all over the place. People made copies of it, and then they were enlightened and started to work on aspects of physics. Okay? Now, it turns out we've been doing that for a while. Isaac wasn't the first, and he's not the last. This is really how science is disseminated today. All of us on this panel write things about, when we have our new discovery, our new result, as Rush mentioned, it goes in a conference paper or a journal paper, or we eventually write a monograph about it and post it somewhere. And so not surprisingly, people over time have collected these monographs, and that's why we have things that look like this. This is the Stanford Library. So over the last millennia, every town, village, city, university has been collecting all of this information, all of these writings from different scientists to try and understand what's going on in the, in the universe really broadly. So relatively recently, something happened about 10 years ago. All this information started going online in massive droves. And one of the more recent efforts, one of the more popular efforts, is Google Books. Okay? So now, with the advent of Google Books, you can enter in a couple of keywords, and back comes, Isaac Newton's great book, even translated into English for you. Okay? And this is a really amazing thing for science. I don't think there's a scientist today who can get by without online resources. I mean, we're using them constantly, and every single day, every single hour even. You can get this on your phone, your tablet, your laptop. It's really just amazing. So now, the world's scientific knowledge is really accessible in a way it's never been before, and this is a great thing for science. But maybe I'm a complainer, that's why I became a researcher. It's still not as perfect as it should be. Okay? And one of the problems with this is that we're still human. Okay? So the Kindle has made sure we don't have to carry physically all of our books around. But still, you have to, as a human or a scientist, if you want to know about something, you have to read all of those texts that have been produced for you over the last 100 years to have a sensible knowledge of what's going on. And we're simply limited by the bandwidth of our eye and the bandwidth of our brains to be able to suck in all of that information. So we're left in this strange situation. All of the world's knowledge is accessible to us. We can enter in a few keywords and get it on our phones. But somehow it's just not readable. It's not really summarizable in the way that we need to be able to draw conclusions about the world's big problems. Like, for example, the problems that Russ was talking about earlier. So some people have drawn an analogy here with the universe. Right? So the universe is made up of visible matter, about 4% of it. Then there's this huge mass of energy and matter that's out there that we call dark matter, which is the 96%. And this is sort of an analogous to what we're doing with data today. And people call this dark data. It's this great mass of data that we know is out there, but for whatever reason, we can't access it, we can't digest it, and as a result, we can't make use of it. So this is a situation that we find ourselves in today. Now, making this problem even more pressing, today's pressing problems often require macroscopic knowledge. They require the ability to assemble all those data points that are out there, as Russ mentioned, search logs and different parts of the literature, and bring them together for when the next generation of really interesting insights come about. So we need this macroscopic knowledge. We need something to read for us. Okay? So we work on problems in a bunch of different areas. For example, things in climate and biodiversity. You would love, if you were a paleobiologist, and I know some paleobiologists, you would love to have the entire fossil record laid out for you so you could understand every die-off, every interaction between species throughout time. A lot of that is published, and we don't have access to it. Problems in health, Russ covered this in great detail. Electronic medical records to all of the drug interactions and diseases that people have published all over the place. And finally, things in financial markets. Russ mentioned before that people are using signals like social media and other kinds of text that are out there to predict drug interactions, and foodborne epidemics is another one that's come across my desk. And also things like the financial markets. We know perilously little about how all of these macroscopic systems are really operating today. So I'm going to focus on one in particular that I've been working on with some colleagues. In particular, one guy named Shannon Peters, who's a geoscientist and will be joining us out in Stanford very soon. So as a computer scientist, I look at this problem and I say it's a real failing of our field. We've put everything online. We've made it very easy to search. But why don't we have a machine that can read for us? Why can't it do the job? And so what I want to talk about in the next couple of minutes is why that's a very hard challenge, and one that we've been working on, and a lot of other people have been working on over the last couple of years, and have made some interesting progress, and you're already seeing it today. Okay? So let me show you why this is such a hard problem. Okay? So here's a journal article that we would like to read. I don't expect you to read any of the type on it. I'm just going to use it schematically. Okay? So what we would like to do with a journal article like this, it's from one of these paleobiological journals, is we'd like to go into a table that looks like this, and we'd like to extract information from it and assemble it into a large database. So apparently we have a little formatting issue, but basically what I want to do from here is have this location Obora that I found a particular genus, what happens to be a kind of cockroach that's interesting to someone for reasons that escape me. Okay? So they want to extract, they want to go into this table and pull out all of those different references, all the fossils that they were found and where they were found, at what time period they're from, and put that into a large database to begin to ask these questions. Now this is a challenging problem for a machine because it's got to be able to read through this table and do all kinds of visual reasoning. It's got to be able to know that Obora and this particular genus are associated and do all of that extraction. And the system I'm going to talk about later is able to do that. Okay? But I want to put that aside and point out even a different challenge, which isn't in the reading part of it, the physical part, but is actually in the semantic part. Now it turns out that in the data set that we've collected over the last little while, there are 44 different Oboras, okay? Different places that are referred to as Obora. And we'd like to build a very high resolution database that's going to tell us which of those Oboras are we even talking about. Okay, so we'd like to link this extraction with it. Now it turns out that if we were able to read the text of this article, it's right there for us. It's got the GPS coordinates, actually, of the Obora we want. And so if we could read that text, we could put that back together. And what I want to get across to you is that the act of putting this table together isn't just having a machine pass over the glyphs. It's actually reasoning about how to combine this information in a way that makes sense and actually resolve things like Obora to the right entity, the right Obora that it's talking about, in addition to doing all that visual reasoning. And these are the type of systems that we're starting to build today and that are so exciting because they can automate a lot of the grunt work that goes on in building these scientific collections, we hope. Okay, so what we want and what I'm going to talk about in the last part of this talk is a machine that can read and reason for us to try and build these macroscopic knowledge bases, we call them. All right. So these systems go by the name trained systems. It's a relatively recent term. We're still trying to figure out how to call them. They actually come out from a bunch of companies. You've probably interacted with one. Maybe some of you have noticed that when you enter inquiries to Google, you start to get what we call structured results on the side from things like Wikipedia. Maybe some of you have seen the system Watson, which I'm going to talk about next. These are examples of systems, trained systems, that involve data, large amounts of data, and some amount of statistical reasoning in them. Okay? So let's talk about Watson for a second so you understand what I'm talking about. So if you don't know Watson, Watson was this machine that was built by IBM. It's now commercialized as a product called DeepQA. And Watson won Jeopardy. Okay? So if you don't know Jeopardy, it's a quiz show, American quiz show. The questions that they ask, for lack of a better word, are sort of these very intricately worded questions that have sarcasm and puns and rhyming and all kinds of stuff. Sort of a uniquely human quiz show. But lo and behold, this little machine here, over the course of 3 days, stomped this guy Ken Jennings, who had won something like 100 times in a row, and was able to basically destroy him. There's a great article about this. If you want, I can point you to it, that described how worried they were about beating Ken Jennings. The guy was a freak of nature. Okay? Anyway, but Watson won. Okay? So that's great. A machine won at this show. You can debate whether or not this is really artificial intelligence. I don't care. It doesn't bother me. It's useful and interesting, so let's talk about it. The thing that was most interesting to me is the way Watson chose to show people what it was doing. So if you watched it, Watson would show several answers that would come back, and each one of them would have a confidence score, a probability associated with them. And I think that's actually something that inside computer science we've known for a while. It's been a revolution in our field over the last 15 or so years that we've realized that the way to be precise, that a computer needs to be precise, and to reason about all the uncertainty that's out there is with probability or statistics. In fact, my dissertation was about probabilistic databases, right? So we've been doing this for a while, trying to understand what does it mean to build these things. Now, these trained systems, these new generation of systems, almost exclusively have this as their way of reasoning. They use statistical reasoning plus lots of data to be able to answer these rich questions. Now, I want to impress upon you that this is a staggering challenge. So in the system I'm going to show you in a minute or two, we're going to see that we're going to have a random variable, a choice that we're going to have to make about a huge array of things. And the number of choices that we're going to have, the number of decisions we're going to have to make is in the billions. Some of our demos have tens of billions of these little individual choices that have to be made. Each one could be yes or no. But that means that we have to search through this truly staggering number of possibilities, 2 to the 1 billion. That's a number I can't even conceive of how large it is. To put it in perspective, the number of atoms in the visible universe is on the order of 2 to the 300. Okay? That's why this is such an interesting challenge, because we have to search through this efficiently in the time actually it takes you to write a query or for Watson to fire back an answer. Okay? Now we cheat a little, but that's basically what we're dealing with. That's why it's such a fundamentally hard problem. Okay. So I'm going to show you one application of our system, Deep Dive, which is the train system that we've been building for the last couple of years. And Deep Dive is a layer that isn't tied to any particular application, but one application where we had great collaborators and partners was in this paleobiological and climate change. So I'm going to show you some applications over that. Okay. So the goal is very simple. We want to extract everything that we can possibly extract, paleobiologically relevant facts from the fossil record. And what we're given are a bunch of PDFs. Okay. We're going to go and crawl these PDFs. And then we're going to try and make this cartoonish database of dinosaurs, where the dinosaurs lived. My students make fun of me that I like the dinosaur, but I like the dinosaur, so it stays. Anyway, so we read the text, and we create the database. Okay? And now, as I showed you when we were doing that reasoning about that picture, every little pixel that's there, we try and figure out what word is it representing. Should these characters go together to form a word? What part of speech is it? Are these two words actually related? Are they in the same dictionary? Are they not in the same dictionary? And in this way, when we read millions of articles, we'll get up very easily to tens of billions of articles. Now this database is a little bit smaller. We only have around 1 billion of those choices to make. But if we can make them all in a sensible way, we can do this extraction task. All right. So we have actually built with our collaborators several databases that they simply couldn't have built without sort of machine assistance. But we wanted to understand how valuable is this? Could we replace what humans are doing? And it turns out that one of our collaborators was building this database over the last 13 years called a paleo database. Okay? 330 volunteers over the last 13 years, 46,000 documents that they've managed to annotate. Okay? Now this database has been truly transformative for their field. They've published 188 papers that they say couldn't have been published without this. Thousands of papers actually cite this database. But 188 that they say couldn't have been done was this macroscopic kind of reasoning that they couldn't do without this database. 17 of those went to high-class places like Nature and Science. And if you don't know, if you're not an academic nerd, those are like the top of the top. That's like, you really made it when you have a Nature or Science paper. That's like, something you brag about to your friends. Okay? So they built this database. So we decided, hey, let's try and turn our machine reading system on and see what we can do. And basically, instead of 330 volunteers, we had about 2 graduate students. Okay? So we said, what could possibly go wrong? So what happened was we were able to very quickly to read about 10 times more documents. And the reason we're limited by a factor of 10 has to do with publishers, and I'll spare you my rant about publications and open access and all that stuff. So we were able to get about 10 times more documents than had actually been read through the system. Now, what it turned out, which in retrospect was totally obvious, was that humans are extremely lazy in annotating these documents. So even though we're reading 10 times more documents, we got 100-fold more extractions, because no person is going to sit through all of those tables and say, this fossil was found there, this fossil was found there, this fossil was found there. And as a result, the machine got a much, much larger corpus of data. Okay? So this wasn't really, in hindsight, too surprising. But the thing that was surprising, and what brings me to why I have hope in these systems, was a very simple and very preliminary experiment that we ran with some of our collaborators. And we pray and hope that this number comes out. Okay? So what we wanted to validate here was how accurate is the system. So if it makes a prediction, how accurate, 80% of them, 60% of them, how often is it? So what we did first is we looked at the volunteers who were making predictions into the paleo database and compared them to experts. And it turned out that the volunteers were correct about 80% of the time. Okay? Now this is a hard task. I would not get 80% on this, but that's about how often they were accurate. Okay? So we looked at this and we said, okay, well 80%. Even if we get 60, 50, at least we're getting so much more data, you can use some statistical magic to be able to make predictions, and maybe it's hopeful and still useful. What was absolutely stunning, and as a result we had just recently, is that on this particular data set, we actually were in the 90s. Okay? So we were actually able to read this data set and do some of these extractions with extremely high quality. And so for that reason, I don't know that this is going to hold out. We're still in the process of really rigorously validating all of this. But that's why I wanted to share my excitement with you, both about how these systems are built, but also our hope that these trained systems can be used to accelerate at least one little portion of science. Thank you for your time.